For this question, we want to find the point of inflection of the graph of the function f of x equals x square root of x plus 27. We also want to describe the concavity. The point of inflection and the concavity can be found using the second derivative. So we'll need to calculate the first derivative and the second derivative. Before I calculate the derivative, I want to rewrite this function as x times x plus 27 to the 1/2 power. The derivative will be easier to calculate in that format. We're going to calculate the first derivative. And the first derivative, we need to use the product rule because we have x times x plus 27 to the 1/2. So with the product rule, I have the first factor times the derivative of the second factor, which we'll use the chain rule for that. 1/2 is the power, so we'll use the power rule, bring the power down. Leave the inside alone. We're going to take 1 away from the power, so that gives negative 1/2, and chain by multiplying by the derivative of the inside. So that's 1. Derivative of x plus 27 is 1. So recapping so far, we have the first factor times the derivative of the second factor, plus the second factor of x plus 27 to the 1/2 times the derivative of the first factor, which is x. Derivative of x is 1. So we've calculated the derivative, and I want to do a little bit of cleaning up. So I am going to notice that I have common factors of x plus 27, and I'd like to factor those out. And I also notice that I have this 1/2 here, and having a fraction in my expression makes it a little bit hard to simplify. So I'm going to write in the other factor a 2 over 2, so I have a fraction with the same denominator. 2 over 2 is the same thing as 1, so I'm allowed to multiply that. So I'm going to factor out that fraction of 1/2, so I don't have a fraction in my parenthesis anymore. And then I'm also going to factor out a factor of x plus 27, and I want to factor out the lowest power. The lower power is negative 1/2, so that's the power I'm factoring out. So this is my common factor that I'll factor out. And if I look at that first term here, I'm going to factor out the 1/2, the x plus 27 to the negative 1/2, and I'll be left with just an x. From the second factor, or from the second term, I'll be able to factor out the 1/2, so I'll still be left with that 2 in the numerator. And I'm going to be left with a factor of x plus 27, and it's going to be to the first power. Now the way that I get that power is by, let's see, let me use a different color. I'm going to take 1/2 minus negative 1/2, and that gives me the first power there. So then I have 1/2 times x plus 27 to the negative 1/2, and inside those brackets I have x plus 2x plus 54, and that's 3x plus 54 in the numerator, and I'll take this 2 to the denominator, and I'll send this whole factor down to the denominator. So it's 2 times x plus 27 to the 1/2 power. When I send that factor to the denominator, that negative 1/2 turns into a positive 1/2. And now I have the first derivative. So I want to find the second derivative. The second derivative is going to inform me about points of inflection, and concavity. So with the second derivative, I'm now going to have to use the quotient rule to calculate that. So I'll take my denominator, 2 times x plus 27 to the 1/2 power times the derivative of the numerator, which is 3, minus the numerator of 3x plus 54 times the derivative of the denominator. The derivative of the denominator, I have that constant multiple of 2, and that's 1/2 times x plus 27 to the negative 1/2 times 1. And all of this is over the denominator squared, 2 times x plus 27 to the 1/2 squared. So we want to simplify this. So as I'm simplifying this, I'm noticing that I have, again, a common factor of x plus 27 that I'd like to factor out. This time I don't have to worry about the 1/2 because the 1/2 and the 2 cancel. So I'm going to factor out that x plus 27 to the negative 1/2. That's the lower power. When I factor that out of the first term, I've got this 2 times 3, which gives me 6. And I'll have a factor of x plus 27 to the first power, just like before. 1/2 minus negative 1/2 is 1. Then in the other term, I'll have a 3x plus 54 times, and all of that gets factored out. The x plus 27 to the negative 1/2 gets factored out. In the denominator, 2 squared is 4, and x plus 27 to the 1/2 squared will be x plus 27 to the first power. So this factor over here is going to get moved down and then also combined with the other factor of x plus 27. And in the numerator, I'll distribute that 6x plus, 27 times 6 is 162 minus 3x minus 54 all over 4 times x plus 27 to the 1/2 times x plus 27. And this is 3x. 162 minus 54 is 108 over 4. And when I combine these two factors together, I add the exponents. 1/2 plus 1 will be 3/2 x plus 27 to the 3/2 power. So I'll write my second derivative as 3x plus 108 over 4 times square root of x plus 27 cubed. All right, so now I have my second derivative. So when you're looking for concavity and points of inflection, what you need to do is you need to find the critical numbers of f prime, and the critical numbers of f prime are when the second derivative is equal to 0 or the second derivative is undefined. So I'm going to take my second derivative and I will set my numerator equal to 0 because that's going to give me when the second derivative is equal to 0. I'm going to subtract 108 on both sides. That gives 3x equals negative 108. Divide both sides by 3, and I get x equals, I believe, 36. Let me double check. Yes, negative 36. And then if I set my denominator equal to 0, x plus 27, I will get x plus 27 equals 0. Subtract 27 on both sides, and x equals negative 27. So these are potential critical numbers for this function, critical numbers of that derivative. However, we do have some special consideration that we need to make here. Critical numbers need to be defined for the original function. So the critical numbers of f prime are where the derivative is equal to 0 and undefined. However, we're limited to only where the function is defined. So if you'll recall, our original function was f of x is equal to x times the square root of x plus 27. And if we look at this function, it has a domain that is restricted. We can only take the square root of positive values. So if I take x plus 27 and I set that greater than or equal to 0, I'll get x plus 27 is greater than or equal to 0, subtract 27, x is greater than or equal to negative 27. The domain of our function f is negative 27 to infinity. So this x equals negative 36 is outside of that domain, so it's not a critical number of our function. And not a potential point of inflection. So when I'm looking at my number line, I'm going to be restricting my view to only 27 to infinity. So we're not going to consider any values less than negative 27. So we've got our critical number of negative 27, and what I want to do is choose a test point in that interval, and we're going to substitute that test point. So I'm going to pick an easy number like 0. We're going to substitute that test point into our second derivative. So the second derivative at 0 will be 3 times 0 plus 108 over 4 times the square root of 0 plus 27 cubed. This gives me 108 in the numerator. That's a positive number. In the denominator, I have 4 times the square root of 27 cubed. That's a positive number. So my second derivative comes out positive, and that tells me that my function is concave up for that entire interval. So we know for concavity, this function is going to be concave up from negative 27 to infinity. Concave down, there are no intervals of concave down. And a point of inflection is when there's a change in concavity. So we have no change in concavity, so we have no point of inflection for this function. For this question, we want to do a little curve sketching. We want to analyze and sketch the graph of the function, find any intercepts, relative extrema, points of inflection, and asymptotes. If an answer doesn't exist, we'll have does not exist, D and E, for the answer. So for this question, let's start with the intercepts. So I am going to find my intercepts. We find an x-intercept by letting y equal 0. So that would give me the equation 0 equals x over x squared plus 25. I'll multiply both sides by the denominator, and that would give x equals 0, because when I multiply by x squared plus 25, on the left it cancels, and multiply by x squared plus 25. On the left, it's multiplied by 0, so we get 0. So we have an x-intercept at 0, 0. For our y-intercept, we let x equal 0. That would be y equals 0 over 0 squared plus 25. And that's 0 over 25, which is 0. So 0, 0 is also the y-intercept. Okay, so we've done the intercepts. Now we're going to get the relative extrema, and we find the relative extrema with the first derivative test. So we need to calculate the first derivative. I'll use the quotient rule to calculate that first derivative. So with the quotient rule, the derivative is the denominator, x squared plus 25, times the derivative of the numerator, derivative of x is 1, minus the numerator x, times the derivative of the denominator, that's 2x. Derivative of x squared plus 25 is 2x. And this is over the denominator squared, x squared plus 25 squared. So simplifying, I can distribute the 1 to get x squared plus 25, and x times 2x is 2x squared. So copying down that denominator, x squared plus 25 squared, and the numerator, I have some like terms I can combine. That gives me negative 3x squared plus 25 over x squared plus 25 squared. And I think I've made a mistake there. Negative 2 plus 1 is going to be negative 1, not negative 3. Excuse me. So this is negative x squared plus 25. Okay, so I've got my first derivative. And to find the relative extrema, I need the critical numbers. Critical numbers are going to be when the derivative is equal to 0 or the derivative is undefined. So let's set our numerator equal to 0, negative x squared plus 25. That's going to give us the critical numbers for when the derivative is equal to 0. So I will add x squared on both sides. 25 equals x squared. Square root both sides. And I get x equals plus or minus 5. Then I need to consider if the derivative is undefined. So to do that, I'll set my denominator equal to 0. X squared plus 25 equals 0. I'll subtract 25, and that gives x squared equals negative 25. I'll square root both sides, and this time I have square root of negative 25, which gives me plus or minus 5i. Square root of negative 1 is I. So that means that we don't have any more critical numbers. Those i's we don't consider. So the only critical numbers we came up with were plus and minus 5. So in the first derivative test, what you do is you take those critical numbers and any vertical asymptotes of the function and you put them on a number line. So we're going to put negative 5 and positive 5 on the number line. We didn't get any asymptotes. They would have been these numbers here. This is the same denominator from the original function, so we didn't get any asymptotes. So we put all of our critical numbers as well as our asymptotes on the number line. And we're going to choose test points in each interval. And we'll, choose test points, number that's less than -5, like -6. We need a number in between -5 and 5, like 0. We need a number bigger than 5, like 6. These are our test points. So we take our test points of -6, 0, and 6, and we're going to substitute them into the first derivative. That was our y prime. And remember that was negative x squared plus 25 over x squared plus 25 squared. So we're substituting this into the derivative, and all we care about is if it comes out positive or negative. If it's positive, we get increasing on that interval, negative, decreasing on that interval. And I noticed that my denominator has this squared in it, x squared plus 25 squared. So this denominator is never going to be negative. So I really only want to focus on the numerator. That's negative times -6 squared plus 25. That's a -36 plus 25, and that's negative. So we get a negative on that interval, which tells me decreasing on that interval. And we have -0 squared plus 25. That's 0 plus 25, and that's a positive. So a positive on that interval is increasing. And we have -0 squared plus 25. That's -36 plus 25. We get a negative. So a negative on that interval is decreasing. So once I've built my chart with these pluses and minuses, I should be able to find any relative extrema. So I have decreasing on the first interval, increasing on the second interval, and decreasing on the third interval. So that means that when I have a change from decreasing to increasing, that creates a relative minimum, and it's going to be at that critical number of -5. When I have a change from increasing to decreasing, I'm going to have a relative maximum at that critical number of 5. So I've identified the relative extrema. So I have a relative minimum at x equals -5. And I want to find the y-coordinate, and I get the y-coordinate by plugging into the original function. The original function was x over x squared plus 25. That's -5 over -5 squared plus 25. -5 over 25 plus 25. -5 over 50 reduces to -1 over 10. So that relative minimum is -5, -1 over 10. Okay, we have a relative maximum at x equals 5. We're going to get the y-coordinate by plugging into that original given function, which was x over x squared plus 25. 5 over 5 squared plus 25 is 5 over 50, which is 1 over 10. So we get a relative max, 5, 1 over 10. So now we have our relative extrema, -5, -1/10, and 5, 1/10. I just want to go back to our questions and kind of check off the relative extrema. Then we want to find any points of inflection. Now we're going to use the second derivative to find any points of inflection. So we have to calculate the second derivative. So let me write down what our first derivative was. We have it right here. Our first derivative was negative x squared plus 25 over x squared plus 25 squared. So let's write that down. We have the first derivative being negative x squared plus 25 over x squared plus 25 squared. So we need to use this to calculate our second derivative. We'll use the second derivative to find the concavity and the points of inflection. So to calculate the second derivative, I'll use the quotient rule and the chain rule. So the quotient rule, got my denominator of x squared plus 25 squared times the derivative of the numerator. The derivative of negative x squared plus 25 will be negative 2x minus the numerator, negative x squared plus 25, times the derivative of the denominator. Here's where I have to use the chain rule. So I get 2 times x squared plus 25 times 2x. Just slowing down on that part a little bit, I used the derivative of the outside function, which is a power. So I brought the power down and took one away from the power. So this is the first power. I left the inside alone and chained by taking the derivative of the inside. The derivative of x squared plus 25 is 2x. And this is going to be all over the denominator squared. So we have x squared plus 25 squared, and then that whole thing squared. All right, so now what I'm going to do is a little bit of canceling. I notice that I have a lot of common factors. I have x squared plus 25 here, x squared plus 25 here, and x squared plus 25 here. So I have that in every term. So I'm going to cancel. We'll cancel one of them here, one of them here, so that 2 becomes 1. And this is a power of 4, so it becomes 3. So we're going to have negative 2x times x squared plus 25 minus negative x squared plus 25 times 4x. I multiplied this 2 times this 2x to get that 4x. And in the denominator, x squared plus 25 cubed. So in the numerator, I'll use the distributive property and combine like terms. So I would have negative 2x cubed minus 50x plus 4x cubed minus 100x. And this is all over x squared plus 25 cubed. Combining like terms, I'll have 2x minus 2x cubed, 2x cubed minus 150x. Over that x squared plus 25 cubed. So when I'm looking for points of inflection and concavity, I'm going to find let me write out what I'm doing here. I'm finding the critical numbers of y prime. The critical numbers of y prime are when y double prime is equal to 0 or y double prime is undefined. So it's when the second derivative is 0 and the second derivative is undefined. So I'm going to set my numerator equal to 0, and that'll tell me when the second derivative is equal to 0. X cubed minus 150x equals 0. Can factor out a 2x, and that will leave me with x squared minus 75 equals 0. 2x equals 0. X squared minus 75 equals 0. This gives me x equals 0. X squared equals 75. I can square root both sides, and that gives me x equals plus or minus 5 square root of 3. So I've got critical numbers of plus and minus 5 squared of 3. And then just like in the previous part where we were looking at the critical numbers of y, when we set the denominator equal to 0, x squared plus 25 equals 0, we're going to get imaginary numbers. So I'll subtract 25 on both sides, take the square root of both sides, and we get x equals plus or minus 5i. So we don't consider those values. So we're going to build our number line with the 3 critical numbers we came up with. These are potential points of inflection. They're going to be points of inflection if there's a change in concavity. So if it goes from concave up to concave down, or concave down to concave up. So we're going to put those critical numbers on the number line. Negative 5 square root of 3, 0, and 5 square root of 3. And we're going to choose test points in each interval. So I need to pick a number that is less than negative 5 square root of 3. So let me get my calculator. Square root of 3 is about 1.7 times 5 is about 8.6. So I need to make sure I choose maybe, let's say, negative 10. Let me pick a number in between negative 5.3 and 0. And let's choose negative 1. In between 0 and 5.3, let's choose 1. And something bigger than 5.3, let's choose 10. We're going to take those test points and substitute it into the second derivative, because the second derivative tells us about concavity. So we'll take those test points of negative 10, negative 1, 1, and 10, and we're going to substitute those into the second derivative, remembering that the second derivative was 2x cubed minus 150x over x squared plus 25 cubed. And once again, I don't really need to focus on the denominator here because x squared is positive plus 25 is positive. We cube a positive, it'll be positive. So we really need to only test the numerator to see what sign the numerator is. So I'll substitute that negative 10 in. 2 times negative 10 cubed minus 150 times negative 10. I'm putting this on my calculator. Let me go ahead and get my calculator out and show you what I'm typing. Okay, so I've got my calculator pulled up here. Let's go to the home screen and type 2 times negative 10 cubed minus 150 times negative 10. And you can see that that is a negative number. I'm going to do this with positive 10 as well. 2 times 10 cubed minus 150 times 10. This one comes out positive. We need to do -1 and 1 as well. 2 times 1 cubed minus 150 times 1. We get a negative. So negative, negative. Oh, sorry. Okay. Got myself confused there for a second. And let's do -1. 2 times -1 cubed minus 150 times -1. And that is a positive. So I know I did those out of order, but we got a negative, a positive, a negative, and a positive. So this tells me concave down, concave up, concave down, concave up. And anytime there's a change in concavity, so concave down is like this, concave up, concave down, concave up. Anytime there's a change in concavity, it happens right here, we get a point of inflection. Change in concavity, we get a point of inflection. Change in concavity, point of inflection. So we have 3 points of inflection, and we want to write these as ordered pairs. So we're going to substitute these into the original function given to us. So our points of inflection are x equals -5 square root of 3, and the y coordinate, remember our original function is x over x squared plus 25. So we're going to do -5 square root of 3 over -5 square root of 3 squared plus 25. It's -5 square root of 3, -5 squared is 25, square root of 3 squared is 3, so this is 25 times 3 plus 25, -5 square root of 3 over 75 plus 25, -5 square root of 3 over 100, and this reduces to negative square root of 3 over 20. Okay, we have another point of inflection at 0, and that's y equals 0 over 0 squared plus 25, which is 0. And we have another point of inflection at x equals 5 square root of 3. So we have y equals 5 square root of 3 over 5 square root of 3 squared plus 25. This is 5 square root of 3. 5 squared is 25. Square root of 3 squared is 3 plus 25. So 5 square root of 3 over 100, which reduces to square root of 3 over 20. So those are our 3 points of inflection. -5 square root of 3 and negative square root of 3 over 20. 0, 0, and 5 square root of 3 square root of 3 over 20. Okay, so we got points of inflection covered. Going back to our directions. We've done a lot of work. Okay, going back to our directions, we've taken care of points of inflection. Last thing we need to do is asymptotes. So for our asymptotes, I'm going to set the denominator equal to 0. We've done this multiple times and gotten x equals plus or minus 5i. So we have no vertical asymptotes. Then for horizontal asymptotes, we look at the degree of the numerator. The degree of the numerator is 1. and we look at the degree of the denominator. Remember, degree is the highest power on x, so we have a degree of 2. And here we have the degree of the numerator being less than the degree of the denominator. So that means we have a horizontal asymptote at y equals 0. So you could do that with memorization, or you can do that with the limit. You can find horizontal asymptotes by taking the limit as x approaches infinity, x over x squared plus 25. Okay, so if we apply the limit right now, we would get infinity over infinity. That's with direct substitution. So because we got an indeterminate form, I'll try the limit again with a little bit of manipulation. So what I do is I divide both the numerator and denominator by x squared. This gives me x over x squared over x squared, 25 over x squared. This reduces the limit as x approaches infinity, 1 over x, 1 plus 25 over x squared. So now when I apply the limit, I would have 1 over infinity over 1 plus 25 over infinity, and 1 over infinity tends to 0, 25 over infinity tends to 0. So both of these go to 0, and that means my limit is 0 over 1 plus 0, that's 0. So that tells me my horizontal asymptote is y equals 0. So we've got the asymptotes covered now. So the final thing that it states in the problem is to verify with our graphing calculator. So let's take our function and type it into the y equals menu. That would give us x over x squared plus 25. Let's take a look at that graph. And my window, let's change it to, I think if I go to the bottom, I'm going to choose 0, zoom fit. Okay, using that zoom fit feature. It zooms in on the important features of the graph. So I'm seeing here that I have a relative minimum here. So let's see what that minimum is. Second calc, number 3, it's relative minimum. I'll move my cursor to the left of that minimum. Hit enter. To the right of that minimum. Hit enter. It says to guess, let's get closer to that minimum. Enter. And I have -5 and -0.1. And I believe that's what we got for our minimum earlier. So what did we get for our minimum? Earlier we got -5, -1/10. And we get a maximum. So second calc, number 4, maximum. Let's go over to the maximum value. We'll hit enter for the left bound. Hit enter for the right bound. Guess. And there's our maximum 5 and 0.1. That's what we got. Then I'm taking a look at our function here. And we have some changes in concavity. I'm going to zoom out a little bit more because I don't think it's showing it properly. Let's go out to -20 and +20 because I want to show you the concavity So what I'm seeing here is the curve being cupped down. So we had concave down, and then the curve being cupped up. We have concave up, and then concave down, and concave up, which is what we found with our second derivative. So we have a point of inflection along here somewhere where it changes from being cupped down to cupped up. So a point of inflection, that looks like maybe along here. I believe it was like negative 0.8, excuse me, negative 8 point something, so it would be around here. And then positive 8 point something would be around here. You can see it changes from being curved down to being curved up around this point here where it's positive 8. So we verified with our graphing calculator. Thank you for checking out my videos. Have a great day.